Thank you all for being here today. Thanks for that introduction, Matt. So today we're going to be going over some research I've been working on improving risk and resilience-based design guidance for erosion and sediment control practices. So we're going to start with a brief background on both erosion sediment control as well as risk and resilience, and then kind of move into a review of existing design guidance to kind of figure out where we needed to complete that research, and then go into the development of both risk and resilience-based design frameworks, and then touch on some research I've done on improving risk and resilience-based design for rock check dams, as well as go into some conclusions. So let's start with some brief background. So sediment is a major problem that can impact waterways through increased turbidity. Other pollutants are able to bind to sediment, which can reduce location for fish spawning, reduce the capacity of waterways that can lead to increased flooding risk. Construction sites are one of the leading causes of sediment in waterways due to that removal of vegetation that once held that soil in place. And it's one of the leading causes of impairment of waterways, which indicates that they can't be used for their intended use, such as fishing, drinking, swimming, or other recreational activities. So to prevent downstream environmental impacts of erosion and sediment-laden runoff, sites are required to develop stormwater pollution prevention plans if they're over 1 acre in size. These need to address site-specific conditions that can impact runoff rates or erosion. And those requirements are met with the development of erosion sediment control plans and the installation of best management practices that attempt to address those site-specific conditions. So there's various site-specific factors that impact soil loss risk and stormwater loading on practices, including soil erodibility, rainfall rates, slopes, infiltration rates, impervious areas, as well as the cover on the soil. So Barry Fagan, while he's working for the Alabama DOT, he developed a framework for effective erosion sediment control, which is the 5 pillars. These improve upon previous approaches that really only targeted downstream impacts. So these are ordered into decreasing effectiveness and increasing cost. So management communications is the cheapest and the most effective. And that's just ensuring that all stakeholders are on the same page when it comes to expectations and plans. Managing work ensures that construction efforts are done in a way that limits soil dislodgement, such as through the delay or limitation of soil disturbance. Managing water ensures that the flow of water through and around construction projects is facilitated in a way that prevents soil erosion. And then erosion and sediment control are those traditional aspects that can be more expensive and less effective than the other 3. Those efforts can be reduced through the proper management of the other pillars. So moving into risk. Risk is defined as the likelihood of an occurrence of a hazardous event, as well as the impact of failure. The overloading practices due to severe upstream conditions can lead to an increased risk of failure for erosion sediment control practices. And that impacts considered in analysis can be both downstream or upstream of practices, which we'll get into in a little bit. So practice failure modes can be difficult to define. It can be varied by practice, but traditionally in erosion control, they're when erosive conditions cannot be prevented. And sediment control, you can get more into structural failures. Past research has aimed at better define these, especially for like silt fence installations, but many installations haven't had them defined. So resilience is related to risk, and that's the ability to prepare for, adapt to changing conditions and withstand disruptions. There's 4 major factors, which is the ability to resist impacts from weather events, reducing the magnitude or duration of those impacts, having absorptive, adaptive, and recoverability capacity, and then using natural infrastructure for those capacities. So we had 4 main objectives for this research. One was to develop a reliable and implementable risk and resilience-based design frameworks, and then apply those developed frameworks to previously researched silt fence practices to serve as kind of a case study, as well as applying those to rock check dam installations through full-scale testing. And then looking to kind of future research needs for the implementation of these design frameworks. So to complete these objectives, we had an 8-step research plan, starting with a review of existing design guidance to identify gaps in risk and resilience-based guidance and provide information on how we can make practices better. And then investigate other previously developed frameworks to guide the development of these frameworks, and actually developing these risk and resilience-based frameworks, then applying those to those previous evaluated silt fence installations. From there, we'd move on to improving the risk and resilience-based design guidance of rock check dams for the Iowa DOT. For that, we developed a full-scale testing methodology. We completed full-scale testing, and then we applied those frameworks to those results of testing. Additionally, we identified and developed testing methodologies for other research practices that lack that guidance. So from this research, we hope to better quantify risk and resilience in erosion sediment control, identify research gaps that may prevent the reliable implementation of these frameworks, and then generally just improve the risk and resilience-based design of erosion sediment control practices and plans to ensure their effectiveness. So our first step in this process was reviewing existing design guidance. So we reviewed over 170 documents ranging from state specifications, design manuals, and field guides, mostly just looking for design approaches that consider site-specific conditions and aren't just general specifications. And then we highlighted and categorized guidance that we thought was risk and resilience-based. So we found that there were three main design approaches for erosion sediment control, and that's the selection of appropriate practices, the placement or spacing practices, and their sizing. So practice selection can be general or a little more specific. General example would be using a sediment basin instead of a smaller sediment trap for sites of a certain area, or more specific, such as recommending a specific type of erosion control blanket or turf reinforcement mats for slopes of certain steepnesses with certain soil types. This primarily considers conditions where practice would be effective, including the slopes, soil types, drainage areas, and lifespans. We found one communication practice, we can see here. This one's from the Iowa Department of Natural Resource. That's a practice selection matrix that outlines the conditions and applications that different practices are effective in. So practice selection for erosion control typically outlined maximum conditions where they'd be effective. It could be flow velocities or shear stresses or slopes. And then sediment control practices mostly had maximum upstream areas guiding their selection. So the placement of practices was primarily spacing of practices solid in series or just the general location. These can primarily be dependent on slopes, is what we found, such as ditch check and slope interruption spacing, which you can see here. Practice sizing we found was most commonly based on only the upstream contributing area. But similar size areas can have vastly different flow rates due to soil types, impervious areas, and slopes. So this may not be adequately assessing flows. So as a whole, we found that many practices were lacking design guidance, especially for practices relating to communication and work, despite their effectiveness. Practices relating to the management of water had non-specific and limited guidance, such as slope drain sizing being based on that contributing drainage area only, which, like I mentioned, may not actually be adequately assessing the runoff rates. We found that erosion control practices had some design guidance out there, but a lot of it was limited, such as only spacing guidance being based on slope for check dams, without any consideration of other factors. Sediment control practices we found were placement or spacing with some sizing. We found none at all for track out management, despite being on just about all construction sites. And stormwater detention practices, such as sediment basins, are kind of the exception to this, with each practice having numerous components that are designed based on site-specific conditions. So moving on to the risk-based design guidance we found four main categories. Two were about the susceptibility or probability of failure, and then two were about the impact of failure. Found increased susceptibility of failure due to upstream conditions, due to longer required lifespans, as well as increased environmental impact of practice failure, or then safety or property damage impacts of practice failure due to flooding. And a lot of times, more robust practices were recommended when either that impact was high, or if the conditions were found to increase susceptibility to failure. So the most common risk-based design guidance we found was based on upstream conditions. Typically, there's those same conditions that impact our stormwater runoff volumes and sediment loading, such as large drainage areas, erosive soils, high rainfall rates, or steep slopes. Kind of the most common type of guidance we saw was the selection of more robust practices based on those, such as a larger sediment basin instead of a sediment trap if you have a larger upstream drainage area. So we found that erosion control practices had selection that was often based on slope steepness and soil erodibility, both of which can massively influence soil loss risk. And the spacing of structural practices such as ditch checks, slope interrupters based on that sequence of slope. So we also found guidance that regarding the susceptibility failure based on increased lifespans. So it's primarily selection and sizing, and this was due to two things. One of which was the increased likelihood of a disruptive storm event if you have a project with a longer duration, as well as material degradation over time. You may be required to choose a practice that will not degrade as quickly for a longer required use. And then another thing we saw is if a practice was intended to be retrofitted as permanent on a site, a common design approach was using a less frequent, more intense design storm, or another method to increase capacity. So in areas where failure can have severe environmental impacts, more intensive design may be necessary to ensure that that failure does not occur, such as using that less frequent, more intense design storms or adjusting other more specific components. So another impact of failure could be due to flooding, which can impact adjacent properties and human safety, especially on roadways. An example of this is selecting an inlet protection practice with a higher flow-through rate if it's right next to a road to make sure that traffic accidents aren't caused due to standing water. Additionally, stormwater conveyance channels may require a larger capacity when out-of-bank flow can impact neighboring areas. So as a whole, we saw that the limited risk-based design guidance out there was mostly general, with many practices not fully considering risk with regards to site-specific conditions. It's especially notable compared to other aspects of engineering design, such as structural engineering that may have exact probabilities and impacts of failures determined and calculated. So just to touch back on, as we move on to resilience, I want to touch back on those factors. We looked and kind of see if any of that existing design guidance kind of fit into resilience at all. We found some that related to the withstanding and reducing the magnitude of disruptive weather events. It was limited in nature, with most practices having a specific capacity, such as being able to withstand a 2 or 24-hour storm, which may not properly design it for a more disruptive event. We did find, though, that overflow spillways can be used for structural practices, such as sediment basins, other stormwater retention practices or ditch checks, that kind of allow for that withstanding of that disruptive event, while also increasing adaptive capacity by ensuring that these practices don't fail during these disruptive events. We found that a few structural practices have dewatering components that aid in recoverability to ensure stability through multiple storm events. The most common one of these was sediment basins having a surface skimmer or another dewatering component, but these are also only designed sometimes to withstand a certain storm event. There has been some research completed on adding dewatering components to other practices, such as silt fence sediment barriers and inlet protection, but few jurisdictions have actually adopted these methods. We also found that there was some consideration of natural infrastructure, typically through erosion control. That's often completed through natural native vegetation. And kind of incorporating natural infrastructure can increase that infiltration rates and prevent soil loss, which can limit the impacts of disruptive events to downstream practices. So as a whole, we found that the design guidance out there tends to be more general without considering site-specific conditions as much as they should. But we found that some risk-based guidance exists, mostly increasing the robustness of practices to prevent failure if there's an increased probability of failure expected, or if that failure would have severe impacts. We also saw a lack of design approaches that considered resilience, with some increases in adaptive capacity through controlled overflow components or recoverability through dewatering components. So after reviewing this design guidance, we moved on to developing a risk-based design framework. So like I said, there was that evident lack of risk management for erosion sediment control designs. That kind of showed a clear need for that determination of risk. And we can one thing we can use as kind of an example to develop this framework is findings from other previously developed risk frameworks for other aspects of construction or engineering, kind of serve as an example. So these past research on risk has found that there's three main factors to consider. That's the probability of an adverse event occurring, the probability of failure under that event, which can be based on the robustness or vulnerability of a practice, and then that impact of practice failure. So the probability of an adverse event is typically the probability of a storm event, which can vary based both on the design storm in question and the expected duration of use for practice. And these are typically calculated on an annual basis. kind of indicating more research is required to determine probabilities for shorter construction seasons. So the probability of practice failure can be especially difficult to quantify. It can be estimated based on upstream conditions as well as past research. It can kind of be more on the general or specific side. There's identifying local conditions, like if you know you have a higher drainage area, you'd increase that expected probability of failure. There's also numerous types of impact of erosion sediment control practice failure that could be considered. It could be financial due to the cost of increased maintenance or replacement. It could be environmental harm, fines from regulatory bodies, or public perception. I said these can be difficult to quantify or estimate, and then project stakeholders should kind of select their pertinent type of impact that they want to consider. Additionally, for analysis, you also need to consider the impact of non-failed practices, such as sediment discharge from a normal functioning sediment control practice. So we developed a 7-step process for quantifying risk in erosion sediment control. Starting with setting your design parameters, determine how your site conditions may influence failure probabilities, calculating or estimating that probability of failure, determine that impact of failure, both that type of impact as well as calculating the impact. And then from there, you can calculate your overall risk. And if your overall risk is found to not meet acceptable levels, you can redesign practices or implement alternative or additional practices. So the design parameters that need to be set include both the type of practice, the design storm the practice is designed to withstand, the anticipated design length of the practice, the type of impact being considered, and the acceptable risk levels, which this can vary widely project to project or practice to practice. And then that acceptable risk levels may be based on surrounding areas, such as if you have a impaired stream next to your site, or just general stakeholder priorities. So the next step would be determining the effect of your site conditions on practice failure. These can also vary based on the type of practice. You can also model expected runoff and sediment loading, model or estimate to determine how those may impact failure probability. And this can be through both a quantitative or qualitative process. There's numerous methods to predict stormwater runoff. It can be both peak flows and total volume based on your site conditions, which typically drainage areas, infiltration rates, rainfall rates, and impervious areas are kind of those driving factors. You can also calculate your expected sediment loading based on your site conditions. One method for this is the modified universal soil loss equation, or MUSL, which estimates the total soil loss from a design storm based on site and rainfall conditions, including runoff volume, peak flows, soil erodibility, topography, and then any cover practices you have in place. Here's that equation. It considers flows from a certain design storm, as well as those site conditions to estimate a sediment yield or soil loss upstream of your practice. And from there, you can calculate or estimate your probability of failure, which, like I mentioned before, can be based on past research or estimated based on site conditions and expected sediment loading and runoff rates. So from here, you'd also determine, next step would be determine that impact of failure. It could be multiple types of impact. You could put analysis for each, which we'll get into in a little bit with an example. You also need to consider the impact of normal function, such as sediment discharge or maintenance costs. So from here, you'd be able to calculate the overall risk based on this equation that considers the probability of failure due to a certain design storm and the impact of both failure and normal function, and determines the expected impact based on those probabilities. And if risk is found to be at an unacceptable level, there are numerous options that exist to lower that probability of failure and decrease overall risk, including modifying practices, selecting different more intensive alternate practices, increasing redundancy, or adjusting upstream conditions. The most common way would be modifications to practices as a method to lower that probability of failure and overall risk, which can be driven by research as well as existing design guidance. But here's a few examples. Both that design guidance and past research have kind of indicated some of these modifications that can increase the robustness of practices and lower failure probabilities. The modifications can vary both by practice as well as by the threat. An example would be if you have a silt fence and you're trying to lower probability due to stormwater loading, you can reduce post spacing, add wire backing, or increase your T-post weight to prevent failure. So if you're unable to lower risk to acceptable levels through modifications alone, Other practices that are inherently more robust may be recommended, such as using a rock check dam rather than a wattle or another ditch check practice. Another potential solution to lower risk is increasing redundancy through the implementation of numerous installations in series, like you can see here in a roadside conveyance channel. You can also adjust the upstream conditions to lower that stormwater and sediment loading on practices to reduce that probability of failure. This is kind of what that general framework looks like. It can be an iterative process where you calculate risk for numerous types of practices until that risk falls below acceptable levels. So we wanted to show an example of how you would use this framework. Silt fence kind of stood out as the practice to do so due to the readily available data, due to a lot of research being conducted on it. Which this past research has identified a few failure modes, including overtopping, flow bypass, undercutting, and excessive sediment accumulation. And then research has developed modifications to increase performance and reduce the occurrence of failure. The main study we're going to look at was completed here in Auburn a few years ago by Dr. Blake Whitman, who evaluated that existing Alabama DOT standard silt fence under conditions from a average Alabama 2-year 24-hour storm event. And he completed numerous tests that allows us to estimate the probability of failure for these practices, as well as made numerous modifications to the practice. So that first step of that process is setting the design parameters for analysis, which we're going to use the testing conditions from that. So a 20-foot section of silt fence with a drainage area of 0.1 acres, based on that existing design guidance for upstream drainage areas, a lifespan of 1 year, and using a 2-year 24-hour storm event would indicate the probability of the occurrence or exceedance of that storm event would be 50%. And then an acceptable risk. For this example, we're using 5% of upstream soil loss from that storm being discharged through the installation, be about 56 pounds, but that value would need to be set by project stakeholders. So from there, step would be calculating the expected conditions, which these are the conditions used in testing, which are based on average Alabama conditions, both soil and hydrologic. That experimental testing under that 2-year 24-hour storm event found that installation failed in 3 of those simulated runoff events out of 8, indicating an estimated failure probability of about 38%. So from here, you then need to determine the impact of failure. So here's kind of a random issue. There's a lack of research on the sediment capture of failed installations. We have seen that large sediment may be deposited due to flow slowing down as it passes from a slope to a flatter area where a silt fence would be installed. Some testing we did for Nebraska found that this could be as high as 66%. So we're using for this example, an expected sediment discharge of 34% of that introduced sediment for failed installations. We also wanted to take a risk as a cost as well. So we looked at Alabama DOT bid tabs and found that it would be about $6 a foot for replacing a silt fence installation, which $5 of that is the installation of a new silt fence installation, and then $1 per foot of that is the removal of the failed one. So after determining all our factors, we can calculate overall risk. Like I said, we use that storm event probability of 50%, an expected sediment discharge of that failed installation of about 380 pounds, that failure probability of 38%. And we also used a 96% capture rate, which Dr. Whitman found through testing for a non-failed installation. We found 72 pounds of expected sediment discharge due to failed installations, and then about 13.8 pounds of expected discharge due to normal function, resulting in a total about 86 pounds of expected sediment discharge, which would exceed that 55.8 pounds that was defined as acceptable, indicating that existing AU-DOT silt fence would not meet that risk-based design. We also calculated the expected cost of replacement based on that probability, which is about $22.80. But Dr. Whitman then modified that installation to increase robustness through reducing the height of the installation with an offset trench, and then increasing the weight of the posts. And he found that the installation did not fail under that 2-year 24-hour storm event. However, you'd likely want to assume a failure probability of not 0, just based on uncertainties that may lead to failure on a site. So from here, we then recalculated the expected impact. So the expected impact, expected sediment discharge due to failure decreased to about 9.5 pounds due to that decreased failure probability. while the expected discharge at that normal function actually increased due to that decreased probability of failure. Which through this analysis, we found that total expected discharge fell beneath that acceptable level, indicating that this would be more effective design with regards to risk management. And due to that reduced failure probability, it also reduced the expected replacement cost of the installation. So that silt fence design may need to be further adjusted, however, if upstream conditions are found to be more severe than typical, such as a larger drainage area or increased sediment loading. And then potential solutions to this would be to increase redundancy, implement alternative practices, or reduce upstream conditions through other practices, such as upstream erosion control. As a whole, we saw that risk was primarily dependent on the probabilities of a storm event occurring, as well as that probability of practice failure. The impact of failed installations can vary. You need to set acceptable risk levels based on that impact. And then you can compare expected impact to an acceptable risk level. And then if that's found to be above your acceptable level, you can increase robustness, add a lower redundancy, or redesign a plan to decrease that expected impact. So from here, we're going to move on to our the resilience-based design framework that we developed. So that risk management that we talked about can be effective to guide decision-making for an expected storm event. However, we're experiencing more disruptive and frequent weather events that can subject practices to more hazardous conditions and potentially cause failure. There's three main stages of resilience you can see here. There's absorptive capacity, adapt, which is the ability for a practice to withstand the initial impact of the event. There's adaptive capacity, it's the ability to ensure that performance does not drop below acceptable levels during that event. Then there's recoverability, which is that time span of the ability to return to full functionality after a disruptive event. These typically aim to maintain performance at defined performance measures. So there's previous resilience frameworks out there that aim to quantify resilience of practices. Typically have three goals: determining if a system or practice is at risk to failure, quantifying the resilience of practice, and then allow for comparisons. So these previously developed frameworks have used both quantitative and qualitative measures. Quantitative measures can be calculating a loss in performance during that event, which may also use probability of disruptive events in that analysis. And then if data is not readily available, you can use either qualitative or ordinal determinations, which can determine adaptive capacity or recoverability based on general trends of the practice, but this may be less reliable. So in erosion second control, we kind of saw that there wasn't much design guidance for resiliency. These disruptive conditions can increase stormwater runoff volumes and sediment loading that can cause failure or performance losses. And we're kind of primarily looking at absorptive capacity, adaptive capacity, and recoverability for these practices. So absorptive capacity in erosion cycle control is that ability to lessen performance losses at the start of event and not fail, which can decrease through the occurrence of a first flush where you might increase sediment loading right at the start of the storm event. One solution to this is adding redundancy to delay those performance losses. This one we found is a little less pertinent to actually measure than adaptive capacity and recoverability, because if you don't have absorptive capacity and you fail at the start event, you're not going to have any adaptive capacity or recoverability. So adaptive capacity is that limiting a performance loss during the hazardous event. If your practice fails, you're going to show a complete lack of adaptive capacity. Like those other capacities, redundancy can increase. And that main thing we saw in the design guidance was controlled overflow for practices to allow for that adaptive capacity. So recoverability is that ability or time span to return to a set performance. This can primarily be through dewatering methods such as floating surface skimmers, sediment basins, but in general, you can also increase it with regular maintenance and inspections. But one thing to note is that more recoverable practices that may have higher flow-through rates may have lower overall performance. So we developed similar to risk, we developed a 7-step process for quantifying resilience to compare different practices. This can be completed quantitatively, qualitatively, or a combination of both. So the first step is to define your performance measures. This can be selected based on the type of practice, stakeholder priorities, or what data is actually available. You can use multiple different performance measures analysis, but similar to risk, acceptable performance would need to be defined if you're doing a quantitative analysis. So here are some examples of performance measures that can be selected, with some practice having numerous, such as a silt fence and barrier having structural performance, discharge water quality, impound formation, or sediment capture as different performance measures. The next step would be to kind of define acceptable recovery, which these recoverability measures can also vary. They could be a dewatering time, a time to return to an acceptable performance level, or that overall level of performance that the practice is able to return to. And similar to risk, these expectations would need to be set by stakeholders, such as acceptable dewatering times. This may be challenging to define for many non-structural practices. So one of the frameworks we looked at was Cordero et al. In 2014, and he outlined quantitative measures of adaptive capacity, which is effectively a percent change in performance during that disruptive event. And for this framework, the way we're calculating this is a change in performance over that typical performance that you'd expect during a non-disruptive event. And subtract that from 1 to kind of give a adaptive capacity score. And for this, you can use numerous performance measures that can be averaged or weighted based on the priorities of the project. So if you don't have available data, you can use a qualitative approach as well. Here's kind of an example that we propose where adaptive capacity score is based on how your practice falls in these categories. And that adaptive capacity score will be based on the percentage of the maximum points. So if you have for example, a rock check dam that's experiencing some degree of washout or flow bypass on multiple locations, you'd have an adaptive capacity score of 1/3, so about 0.33. Both the number and types of categories for this analysis can be altered based on practices or priorities. So the next step would be calculating recoverability. That's either based on that timeline for return to recovery, performance after disruptive event, or both. You can use a similar equation to adaptive capacity, comparing that loss of recoverability to an acceptable level. You can also use a qualitative method depending on the type of practice and expectations if you don't have that data. So kind of be that same method as the adaptive capacity. And here are just a couple examples of what you could use. So to determine your overall resilience, it would be the sum of that adaptive capacity score and recoverability, range from 0 to 2. A score near 2 indicates a resilient practices. A score under 1 shows you're lacking either adaptive capacity, recoverability, or both. And these can be compared to both other practices or acceptable resilience scores. But from here, you can propose modifications that can help improve the resilience of practices. So similar to risk, you can use modifications to increase both adaptive capacity or recoverability. Generally, increasing adaptive capacity by preventing failure under disruptive events. And then past research, especially on structural practices, has developed modifications that can increase its capacity. And if you're unable to modify to increase adaptive capacity to acceptable levels, you can also, similar to risk, select more robust practices, size practice differently, or increase redundancy. Increasing recoverability can also be dependent on practices. Past research has developed modifications for more efficient dewatering methods, such as a silt fence dewatering board and overflow weir, which you can see here on the right, or a silt fence inlet protection dewatering board, so on the left. You can also increase recoverability through more intensive maintenance schedules. So similar to risk, this can also be an iterative process. If you need to improve if you find that you need to improve either adaptive capacity or recoverability, you can make modifications, recalculate your resilience until you kind of reach an acceptable level. So I want to go through an example of this framework through some silt fence research that I completed for the Nebraska DOT a few years ago. So what we did for this testing was we subjected, after normal testing, we subjected each installation to what we call disruptive conditions. Basically introduce as much flow as we could until we found the practice would either be stable or fail. So we found it didn't fail under those that standard 2-year 24-hour storm that we subjected to, but that Nebraska DOT standard silt fence did fail when disrupted in more disruptive conditions. It shows a complete lack of adaptive capacity that would also result in no recoverability. So that practice would have a resilience score of 0. So to kind of prevent failure, we implemented a 6-inch offset trench that decreased that height of installation, resulting in decreased forces on that installation and prevented failure under those disruptive conditions. We found that increased adaptive capacity, but that overtopping was kind of an uncontrolled manner, which still showed a lack of adaptive capacity, indicating that qualitative analysis would have it be about 0.33. And we also found that the geotextile became clogged with sediment, so that impoundment remained upstream for extended periods of time, showing a lack of recoverability. So another modification that we tested aimed to both increase the adaptive capacity and recoverability, which was a dewatering board with an overflow weir that allows for controlled overflow under disruptive conditions, as well as allowing the practice to effectively dewater. However, when subjected to a disruptive event, we saw that there was excessive sagging in the fabric that led to flow overtopping at the fabric and not at that design overflow weir. So we found that that showed no increase in adaptive capacity from the previous installation. But we did see that effective dewatering board led to effective recoverability, so increasing that recoverability score to 1 and overall resilience score of 1.33. So we made one final modification, which was reducing the post spacing, kind of where you'd have that increased impoundment to limit that sagging and force those excessive flows over that designed overflow weir. We found under disruptive conditions, it did overflow where we wanted it to, into that energy dissipation pad of a wattle, which increased that adaptive capacity score to 1 and a resilience score of 2.0, indicating this was a much more resilient practice than that initial Nebraska DOT standard. The quick summary of work we did on resilience, we found that the key pertinent design aspects for erosion sediment control are the adaptive capacity and recoverability. Based on that design guidance, we found an evident lack of resilience-based design guidance. So we developed a 7-step process to better quantify the resilience of practices. Found that past research shows that modifications can increase adaptive capacity and recoverability, such as effective overflow and dewatering components. But future research is required to better quantify resilience capabilities, such as using those quantitative processes. So from here, we're going to touch on some tests I did recently for the Iowa DOT on improving their rock check dam standards, which we also use to increase their risk and resilience-based design guidance. So a rock check dam is installed, typically an installation of rock installed in channels to lower risk of erosion due to slowing flow through formation of impoundment. These are inherently more resilient than some other ditch check practices due to their being recommended in use for in channels with higher expected flows. We also found that design guidance for rock check dams is limited despite their widespread use. We found them in effectively every single manual we looked in, but there was really no site-specific guidance outside of their spacing. So for this research, we evaluated that existing Iowa DOT rock check dam standard. We developed cost-effective and more efficient modification enhancements that both decreased soil loss risk as well as increasing resilience. So we did a literature review with this. We developed our testing methodology, conducted experiments, and then used the results of that experiments to develop recommendations. So our literature review had 2 main objectives, which is reviewing existing standards, as well as analyzing the results of past ditch check testing to both develop our methodology and identify potential modifications. So we found that rock check dam standards can vary widely in components. However, most of these are similar to the Iowa DOT standard installation, which was a large rock, 2.5 feet tall with a 6-inch weir for effective overflow in the middle. We saw that some employed components to increase impoundments, 2 with geotextile overlays and 11 with a smaller choker stone in the upstream face. We also looked into some of past research, which mostly was on other practices such as wattles. So through field testing, small-scale testing, and large-scale testing. So we found in our literature review that there's a clear disconnect between rock check dams commonly used and then prior performance testing, which indicated that you require a geotextile or smaller choker stone over the upstream face to actually facilitate impoundment, but very few actually use these. Just kind of briefly, we're going to touch on our testing methodology before getting into results. So we evaluated a standard installation followed by 7 modifications. Each was evaluated 3 times under a low flow and a high flow. That high flow was representative of 1 acre in Iowa, and that low flow was about half an acre. So here's our rock check dam testing setup. Flow is pumped from a supply pond into a tank with a calibrated weir that we can use to reach our required flow rates. We installed string lines every 5 feet upstream and downstream, serving as measurement points. We found a maximum theoretical impoundment of 63 feet, found through a survey. It's effectively how long that impoundment would be if the rock check dam impounded to that effective height. We primarily were looking at hydraulic testing with some sediment-laden testing after. Measurements we're taking are flow depth and velocity at 3 locations at each cross section. To kind of generate a flow profile, a location of the hydraulic jump, which kind of that length of impoundment, and where that flow begins to slow to non-erosive levels, as well as dewatering time to see if there are any recoverability issues. So after hydraulic performance, identified a most feasible and effective installation. Both that and the standard were evaluated under sediment-laden conditions, determine improvements in both sediment capture as well as in water quality. So we evaluated the Iowa DOT standard installation as well as 7 modified installations with adjusted components, including removing the excavation underneath, using a smaller gradation of rock, implementing a geotextile overlay, adding dewatering holes in that geotextile overlay to increase recoverability, and then reducing that bottom width perpendicular to flow. So all these aim to either lower costs, increase performance, or both. So here's that Iowa DOT standard installation. It uses a large rock, a geotextile underlay, 6-inch excavation underneath, but no overlay or choker stone to increase impoundment. So evaluated 7 modifications with a combination of those modified components. All of these were developed iteratively based on the results of previous tests. Here we're going to go to some of our hydraulic testing results. So we found that the standard installation was highly ineffective at reducing flow velocity for much of that channel. It only reduced flow velocity immediately upstream of the installation. And we saw that over 90% of that channel was still subject to those high velocity erosive flows. So this was only able to form small amounts of impoundment due to large voids between rocks for the installation. So of all the modifications we developed, we found that installations with similar components, especially that geotextile overlay, performed very similarly. We found that large rock alone in that Iowa DOT standard, as well as that standard rock gradation installed on grade with no excavation, was unable to form impoundment for much of that channel. Using a smaller rock gradation that reduced those void size increased that impoundment to about half the channel. We saw that you really needed that geotextile overlay to protect most of the channel. We also saw that even the highest performing installations were unable to reach that theoretical maximum impoundment. The theoretical maximum impoundment would also be where an upstream practice would be located based on spacing guidance. So one thing we looked at was the flow velocity through the channel. So a few things we notice here is kind of that all those installations with that geotextile overlay perform similarly, as well as those installations with a large rock alone being ineffective at slowing velocity for much of that channel. We also saw that flow velocity immediately jumped to erosive conditions downstream. We did see that for highly erodible soils, that flow velocity would be at erosive levels, indicating a potential need for an additional erosion control practice. So kind of our hydraulic testing conclusions were that addition of a geotextile overlay reduced the risk of erosion for much of the channel. Erosion risk still exists immediately downstream and in areas with highly erodible soils. Smaller rock allows for more controlled overflow under disruptive conditions. We kind of having a more effective weir height. With that larger rock, the geotextile overlay, we saw that there were kind of gaps that allowed flow to overtop at one spot instead of over that entire weir, which also reduces the effective height of the installation. With the geotextile overlay without dewatering holes, we saw extensive dewatering times. So we added dewatering holes in that geotextile overlay to increase recoverability capacity. We also found that did not adversely impact performance at all. We're also going to briefly touch on our sediment retention testing results. So that standard installation, due to that lack of impoundment, only captured about 9% of the introduced sediment, while that most feasible and effective installation increased that to about 72%. That increased impoundment also decreased that discharge turbidity compared to the standard as well. So as a whole, we saw that installation with no excavation, a smaller stone gradation, a geotextile overlay with dewatering holes, and a reduced width was chosen as the most feasible and effective installation due to reduced cost as well as increased performance, which has increased that performance from 6 feet to 58 feet, increased sediment capture by about 7 times, reduced discharge turbidity, and it was about half the material cost as well. So we wanted to apply that risk framework to this testing. So that standard installation showed a failure under all conditions due to the lack of impoundment. So we assume that to be 100% probability of failure due to those large portions of the channel being unprotected from erosive flows. We found that most feasible and effective installation would reduce that probability of failure, as well as the impact of normal operation through significant increases in sediment capture and erosion prevention, as well as decreased discharge turbidity. We also would assume that would have a low probability of failure due to we didn't see any washout under any conditions, even with that small rock, as well as that inherent robustness of rock check dams compared to other practices. We found that those modifications, especially that geotextile overlay, decreased expected impact due to erosion prevention and sediment capture. We also wanted to apply our resilience framework to it as well. So for that standard installation, we saw a lack of adaptive capacity due to that lack of performance under all conditions, especially disruptive conditions, which would have an adaptive capacity score of 0. We did see recoverability because of those high flow-through rates, so that would have a recoverability score of 1 and a resilience score of 1 based on those. The geotextile overlay with a smaller rock gradation, but without the dewatering holes, increased adaptive capacity to 1.0 by allowing performance under disruptive conditions and having controlled overflow. But that would reduce recoverability to 0 due to slow dewatering due to that geotextile overlay becoming clogged with sediment. But the addition of dewatering holes, we saw no performance loss, which allowed that adaptive capacity to remain 1. And then that effective dewatering increased that recoverability to 1 and that overall resilience to that score of 2 that we're looking for. So overall, through the development of these, we saw that more research is necessary to better implement and more reliably implement these risk and resilience-based design frameworks, including determining more accurate storm probability data based on practice lifespans, especially for projects that are under a year. Better determining practice failure probabilities, better quantifying the impact of failed practices, such as that silt fence we talked about, being able to capture sediment even though it failed, as well as gathering performance data during disruptive events, and then better definitions of acceptable performance and recovery. So as a part of one of these projects, we did propose some future research at our Auburn University Stormwater Research Facility, including the analysis of regional and seasonal rainfall conditions for limiting soil disturbance, optimizing construction scheduling, and effectively managing work, which could also help generate storm probabilities for product lifespans. Modeling of vegetative buffers and sediment capture, which can help increase redundancy for sediment control plans, as well as incorporating natural infrastructure. The performance of alternative sediment barrier practices, and then performance of slash mulch berms and inlet protection and ditch check applications. These two would be helpful in generating failure probabilities and determining the flow rates at which these practices would fail. So as a whole, we saw that there was an evident need for increased risk and resilience-based design guidance. We found that we were able to quantify risk through storm event probabilities, practice failure probabilities, and the impact of failure. And then both research and existing design guidance can be used to propose modifications to increase robustness and decrease that probability of failure. We also found that we can measure resilience both quantitatively and qualitatively through measures of adaptive capacity and recoverability to allow for comparisons, as well as using those modifications to increase resilience. We also found that future research is necessary for the reliable implementation of risk and resilience-based design frameworks. And one thing we have coming up in May at our Stormwater Research Facility that I wanted to plug is our Stormwater Week, terms of our installer training, as well as our road sediment control field day. And with that, I first wanted to thank the Iowa DOT and the National Cooperative Highway Research Program for their financial support of this research. And I think we should have time for some questions.
Awesome. Thank you, Brian. That was very informative. So looks like we have a Q&A at the bottom. So for folks who have any questions for Brian, please open up that Q&A tab to ask your questions. And then Brian, are you able to see that Q&A tab at the bottom of your screen?
I don't think so with my presentation up. We had one person ask the dates for the Stormwater Week. I think that's May 12th through the 14th. Is that correct, Matt?
Yes. Yep, May 12th through 14th. And so, yeah, that'll be our Stormwater Week. I'll be sure to send out everyone who's gotten the email about the Tiger Streams will also get updates about the Stormwater Week. So if you're watching this webinar, we'll make sure to add you to the master mailing list and keep everyone up to date about Stormwater Week. That'll be May 12th through 14th. So Brian, I guess oh, we have a question. Great. Are you able to see that, Brian? Looks like
I can, yes.
Okay.
Yeah, so Nick asking if we have approximate cost for the for that rock check dam MFDI compared to the standard. We did an approximate material cost estimate. I don't have those numbers in front of me. I should have included them. My apologies. But I know it reduced material costs from about $600 per installation to closer to about $350. And then he also asked if we have any drawings for that MFEI configuration. I believe that final report is published. So if you search Iowa DOT rock check dams, that final report should come up for that project. That'll go into more detail about that testing and better describe that MFEI.
Brian, could you discuss more about where this research is headed, sort of what future research might look like?
Yeah, so this project, that most of this risk and resilience work was for that NCHRP project. So it's a 3-year project that aims to increase the risk and resilience-based design guidance and erosion sediment control. So all this stuff was kind of for that first phase, which was where no testing was conducted for that project, but we were able to apply that Iowa DOT stuff to it. So what we did was we proposed, kind of based on our literature review of existing design guidance and kind of the development of those frameworks, we proposed a few research projects to our project panel, which is composed of people at numerous DOTs from around the country. And from there, we proposed that research. They selected which ones they thought were pertinent, that they would like to see data for. And then over the next year and a half, those tests will be completed. I mentioned a few of them. Another one I didn't mention is we're also doing research on development of guidance for temporary slope drains as well. Yeah, from there, over the next year and a half, we should, after the project's over, all this information should be published. I'm sure there'll be more webinars in the future for other people that are on the project, discussing more about it.
Cool. All righty. Looks like I don't know, we might have somebody asking a question. I think I see, Brian, I'm sure you see that. Looks like a half question, which was maybe submitted before the thought was fully developed. So we'll see if anybody else has any other questions. For those of you who, oh, so we got a question there.
I believe, Matt, the recordings get posted.
What was that?
The recordings, John's asking if the recordings of this webinar as well as other ones are posted anywhere.
Yeah, absolutely. There's going to be a link on the follow-up email, but I'm just going to go ahead and throw the link in the chat right now. Oh, webinars. So we have a YouTube page for the person who's asking. We have a YouTube page that holds all of our videos, not just our TigerStream webinars, but any sort of informational videos that we have or outreach videos. It's all, if you just type in Auburn Stormwater on YouTube, and I am posting the link in the Oops, that was just to the panelists. Let me send this to everybody. Okay, so to see all of our previous webinars, Brian is our 15th guest speaker, so we've got 14 others. You can follow that link that I included in the group chat or in the webinar chat, and that'll bring you to our YouTube page with all of the other stormwater webinars. And please feel free to check out our other videos while you're on our YouTube page. Okay, we have just a couple more minutes left, so we'll give it just another few seconds here. As I mentioned before, Brian is close to graduating, so he's got another few weeks left as a PhD candidate here with Auburn Stormwater, and he'll be, defending this research again soon. Looks like we have another question here, Brian, if you see that.
Yeah, so Jacob's asking, discussing the calculation or approximation of a technical risk a little bit more, and how it recommended given locality or jurisdiction make such an assessment. It's a great question, Jacob. That's one thing I kind of wish we'd looked into a little bit more, potentially through a survey of DOTs or regulatory bodies. Kind of the example I did, I just kind of made an approximation. But given locality or jurisdiction, kind of make that assessment based on a big thing would be if there's a presence of a protected natural resource nearby, kind of reduce that acceptable level of risk. But a lot of it's going to be based on the stakeholder priorities. Could be the ownership, the contractors, the local regulatory body, or even just the local community.
Alrighty, well, I think that'll conclude our webinar today. I guess while I'm doing this outro, if there are any last minute questions, feel free to throw them in the Q&A. Brian, if you don't mind sharing your email address in the chat.
Yeah.
And that way, for folks who might have some additional questions, you'll see Brian's email popping up in the webinar chat there. Feel free to copy that and reach out if you have any questions down the line. As I mentioned before, there will be a recording of this webinar. We'll send that out in a couple days once it's done being processed and all that. So keep your eyes out for the follow-up email, because that is also how you will acquire your PDH for attending the webinar today.
Matt, I don't know if I'm able to message everyone. You just might need to copy what I sent you. And
oh, I see. Okay. All right.
Yeah, feel free to reach out if anyone has any questions about the presentation. There was a lot of information I went through fairly quickly.
So everyone should be able to see Brian's email there. Again, thank you all for attending. Keep your eyes peeled for a follow-up email from us for how to get your PDH. And May 12th through 14th is the Stormwater Week. Again, by being on this webinar today, you'll be added to our master mailing list, and any updates for Stormwater Week or other events coming down the line, you'll be receiving those notifications. But okay, Brian, thank you again for presenting today, and everyone, have a good day.
Thank you.